Next we'll work a for-practice problem. Find the hydronium ion concentration of a 0.250 molar hydrofluoric acid solution. So this is similar to the problem that we just did. We'll need to write our balanced equation. We're going to use that to set up an ice table. We're going to use our ice table, the equilibrium row, to set that equal to the Ka for hydrofluoric acid, solve for X, okay, and then use that to calculate our hydronium ion concentration. So let's get started. Hydrofluoric acid is HF, and here's how we write the dissociation equation. Hydrofluoric acid plus water, and in this case the water will be acting as a base, dissociates to H3O plus F minus. And because hydrofluoric acid is a weak acid, we can't simply use the initial concentration and plug that in to find the pH. So we'll need to calculate the hydronium ion concentration by setting up an ice table. So here's how we set up our ice table. ICE stands for initial, change, and equilibrium. So we start with our amounts that were initially given, and the only amount that we were given initially is the 0.250 molar hydrofluoric acid. So we're going to plug that in here. Okay, we don't care about the water because it's a liquid, so we don't consider that in our ice table. We assume that initially we have approximately 0 of the H3O plus and 0 of the F minus. So we're losing X of the HF, gaining X of the H3O plus, and gaining X of the F minus. How do I know that? Why did I not need to calculate Q? Because I initially have a concentration of 0.250 molar, and I'm trying to determine what my amounts will be at equilibrium. So if I initially put in 0.250 molar of hydrofluoric acid, then the reaction can only move toward equilibrium from that point, and so therefore I know I'm losing my starting material as that ionizes and gaining product. So at equilibrium I will have lost X from my 0.250 molar, so I'll have 0.250 minus X, and I'll have X for my H3O plus and X for my F minus. Now I can set up my K expression. So K is equal to H3O plus times F minus over HF. Remember, it's products over reactants at equilibrium, so my equilibrium row right here. So now I can plug the values in for my equilibrium from my equilibrium row, and I have 6.8 times 10 to minus 4. Where did I get that number? This is the Ka for hydrofluoric acid. So you're going to look that up in a table if it's not given to you. And then I have my H3O plus, which was X, and my F minus, which was X. Okay, so that's from this X and this X, divided by 0.250 minus X, and that came from right here. So you take the values from your equilibrium row and plug them in. So that gives me 6.8 times 10 to minus 4 equals X squared over 0.250 minus X. But since the Ka for HF is 10 to minus 4, I might not be able to assume that my X is small here. So if I want to save time, I might just go ahead and work my quadratic equation. Now there are a couple of different ways I can work this problem to solve for X. I could multiply both sides by 6.8 times 10 to minus 4 and then distribute across the 0.250 minus X and so forth, but that will make the problem longer. So I'm going to use a little shortcut method to do that. I'm going to say that I can rewrite this as what? 2.250 minus X equals 1 over 6.8 times 10 to minus 4 times X squared. So in other words, I know that there's a 1 in front of the x essentially, and I can call the coefficient of x squared 1 over 6.8 times 10 to the minus 4, which reduces a little bit of my math by making me not have to distribute across everything. Now I'm going to rewrite that into the quadratic form, so I get, if I move the 1 over 6.8 times 10 to the minus 4 to the left, I get 1 over 6.8 times 10 to the minus 4 times x squared, okay, plus x minus 0.250 equals 0. Why? Because I changed the sign on everything. So when I move this to the left, I had a negative 1 over 6.8 times 10 to the minus 4. So I changed the sign on everything, and I have it now in the quadratic form. So now I can plug into the quadratic equation. This is my A, 1 is my B, and this is my C. So remember the quadratic formula. X is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So now I'll plug everything in. X is equal to minus 1 plus or minus the square root of 1 squared minus 4 times 1 over 6.8 times 10 to the minus 4 times negative 0.250, okay, all over 2 times 1 over 6.8 times 10 to the minus 4. So I rewrote that for clarity, and if you work all of that math, you get x is equal to minus plus or minus 38.361 over 2941, and that means x is equal to 0.01270 or negative 0.01338. We know we can't have negative concentrations, so that throws out the second candidate, which is going to be true for most of these problems, if not all of them. And so x is equal to 0.01270, which is equal to our H3O plus concentration. And so, well, if we're considering our sig figs, that's equal to 0.013. And so if you wanted to calculate the pH, you'd just take the negative log of that, and you'd have the pH of your solution.